we've seen that if we were in R3, that we could express a line through three equations that were called the parametric equations. Now notice that each of these parametric equations were themselves individually just the equations of lines in the variable t. Then what we did is we said, well, what happens if we changed those? And instead of letting them be lines, just let them be anything they wanted to be. And all of a sudden, we got the idea of a parametric curve. Suddenly, our lines were free to bend and coil and curve around. Now, in the same spirit, we've seen that a flat plane in Euclidean space can be expressed as an equation of the form ax plus by plus cz equals d, a single equation in three variables. So what happens if we allow this to be any equation in three variables? Would it have the same effect? Would you get a curvy surface instead of a flat plane? Well, that's what we want to investigate right now. Let's start off with a specific equation. Say x squared plus y squared plus z squared is equal to 4. Does this one equation describe a surface? And if it does, what kind of surface does it describe? Well, maybe one way to attack this is to be clever and to recognize that this right here was exactly rho squared when we write things in their spherical coordinates. And so this is the equation rho squared equals 4. But since rho is always positive in spherical coordinates, this just means that rho is 2. So this is the same thing as the set of all of the points whose rho value in spherical coordinates is 2. Now remember that rho describes the distance of a point from the origin. Now if we were to mark some tick marks, so I have some sense as to what's going on, including an axis running down here, in the plane the set of all points whose distance from the origin is 2 consists of a circle. But since this is a three-dimensional analog of that, it makes sense that this is the graph of a sphere centered at the origin of radius 2. And so there's our sphere of radius 2. That only worked because I recognized the spherical coordinates. Is there any other way that we could have got that this was the graph of a sphere without recognizing spherical coordinates? Here's a slightly different way to attack the same problem. Let's imagine taking this unknown surface and slicing it with a bunch of planes, say planes parallel to the xy plane. So we'll slice it right here, and we'll slice it at a plane 1 unit above, and we'll slice it at a plane 2 units above. And we'll just keep slicing the surface, trying to see what it looks like in these individual slices. Now remember that each one of these slices is a plane. The xy plane is the equation z equals 0, and each of the other planes would be given by z equals a constant, where that constant represents the height above or below the xy plane. Now how do we see what each one of these slices looks like? Let's focus on the z equals 0 slice first. If z is equal to 0, we could plug that into this equation, and so the z equals 0 slice would look like x squared plus y squared plus 0 squared is equal to 4. That's x squared plus y squared is equal to 4. Or x squared plus y squared is 2 squared. And so that's the equation of a circle of radius 2. So if I were to take a top-down view of the surface, looking straight down the barrel of the z-axis, then what I would see is if I were to highlight only that one slice, the slice in the xz plane, I would see a circle of radius 2. Well, what about height 1? So if we plug in z equals 1 into here, we'll get the equation x squared plus y squared plus 1 squared is equal to 4. So that's x squared plus y squared equals 3. Or the square root of root 3 squared, which means that we have a circle here of radius square root 3. So square root of 3 is about 1.7. And if I were to mark that in this picture here, this would be the picture I would see looking straight down the z-axis if I only saw the points at height 1. And I could repeat this for every other set of points. At height 2, we'd have the equation x squared plus y squared plus 2 squared is equal to 4. That's x squared plus y squared equals 0. That's a circle of radius 0, which means the minute I get up to height 2, I just see a single point. There's only one dot at this particular height right here. In fact, if I tried to go any higher, say I tried to go to height z equals 3 and plug it into here, we'd get x squared plus y squared plus 3 squared is equal to 4, or x squared plus y squared is equal to negative 5, and that's just not going to give me any points at all. On the flip side, if we were to look 1 unit below the plane, we'd get x squared plus y squared plus negative 1 squared equals 4. Well, negative 1 squared is 1, and so we're back to x squared plus y squared equals 3, which means at a height of minus 1, I'd see the exact same curve I saw at a height of 1. So what does this mean in terms of my picture here? Well, what it means is, imagine taking each one of these curves in the xy plane and drawing them at their appropriate height. So at height z equals 2, I will simply draw one dot. And then I'll eliminate that plane. Next, at height z equals 1, I'll draw a circle of radius 1.7. So let's say this is 1, 2. So 1.7 would be here. And I'll do my best to draw a circle in this plane of radius 1.2, and then I'll eliminate the plane. At height z equals 0, we had a circle of radius 2. So at z equals 0, I'll draw a circle of radius 2 in the plane. So I'll do my best to sort of trace a circle in this plane. You notice it's sort of going to be underneath the circle I drew above it here. And then I'll get rid of my helping picture of the xy plane. Finally, at the depth, z equals 1, so that's 1 unit down here, I'll draw a circle who should be parallel to the circle above, so it should look something like this, because remember, it's the same radius as that dark blue circle. And if we would have gone 1 point lower to depth 2, we would have found a single point. And so if we remove all of the helping planes, then I have a picture who looks like this. A series of concentric rings piled above each other. If I were to add more heights, then I would start to see circles who would fill in all of these missing places in between, and I would start to get the impression of an object who is circular all the way around. And so once again, it seems as though we're looking at a sphere centered at the origin of radius 2. So this is a pretty useful graphing technique. These curves that we got, by taking slices through these various parallel coordinate planes, are called the traces of this object. So these would be called traces in Z, or traces parallel to the xy plane. Now I'm going to be the first to admit that trying to take these two-dimensional traces that we drew and then draw them in three-dimensional space at the right heights to visualize a surface is, well, hard to do by hand. However, if you have access to machines, we can at least illustrate the basic idea. Here are those same level sets, but now I'm having Maple be able to render them at their appropriate heights. And so you can kind of see this direction that they were completely horizontal slices. But with all of this context in here, it's much, much more likely that this object is probably a sphere. In fact, we could have Maple fill in the blanks. And if we do that, we can definitely see the sphere with those traces. And when we remove the traces, it's now even more obvious that we're looking at a sphere of radius 2. Let's take the ideas in the previous example and put them on solid ground. We define a surface in R3 to be the graph of a single equation in 3 variables. So you'll have some formula that has x's and y's and z's, and that formula will generate some kind of surface in 3-dimensional space. A trace of the surface is the plane curve found by setting one of the variables equal to a constant. Intuitively, it's what we get when we slice the surface with a plane parallel to one of the coordinate axes. For example, if we were to set x equals 0 in our formula, we would be taking the plane x equals 0, which is the zy axis, and we would be slicing it through the surface. And the trace would be the curve we get by making this slice. If instead we set y to be 1, then we would be taking the plane y equals 1, so parallel to the xz plane, but 1 unit forward. We would be slicing this plane with the surface, and that would get us another curve. And this curve would be called the y equals 1 trace. As we saw in the previous example, by piecing together many traces, we might be able to see just what our surface looks like. So let's try this out on an example. Plot the surface x squared plus y squared minus z squared equals 1. So I'll put up some coordinate axes in three-dimensional space, but I don't think I'm going to use them just yet. I'm going to go and try to set up what my traces might look like. So let's look at a bunch of the z traces. So if z is equal to 0, we're going to get x squared plus y squared minus 0 is equal to 1. And so that would be a circle of radius 1. So I'll draw some of these traces down here in some just helper space. So x, y. When z is equal to 1, I'm going to see a circle of radius 1. Or sorry, when z is equal to 0, I'll see a circle of radius 1. When z is equal to 1, we're going to see x squared plus y squared minus 1 equals 1. Or x squared plus y squared equals 2. So that would be a circle of radius 2. So I'll see a circle out like this at z equals 1. If we do the z equals 2 trace, we'll get x squared plus y squared minus 4 equals 1, or x squared plus y squared equals 5. So that's a circle of radius square root 5, which is about 2.2. And that would be the z equals 2 trace. And lastly, if I did z equals 3, we'd have x squared plus y squared minus 9 equals 1, or x squared plus y squared is equal to 10. So the square root of 10 is a little bit more than 3, and so what we're seeing is we're seeing concentric circles expanding outwards. Well, what about traces who are below the x-axis? Or below the xy plane, sorry. Well, just notice that these traces are the same whether we do positive or negative z values, because z is squared. So let's try to put this together in a series of traces. So I'm going to go and draw a couple of planes to help me out here. So this will be the z equals 3 plane, the z equals 2 plane, the z equals 1 plane, the xy plane, the z equals minus 1 plane, the z equals minus 2 plane. At the z equals 3 plane, we're going to draw a circle who has a radius of a very big circle, a circle of radius more than 3. So I'm just going to try to draw it as big as I can to fit here. And then I will eliminate that plane. At height 2, so this tick mark right here, we're going to draw a circle who has a radius of 2. So it'll be about that much longer. Oops. And then I'll get rid of the z equals 2 plane. At height 1, we had a circle of radius 1. Sorry, at height 1 we had a circle of radius root 2. And so that will be a little bit smaller than this circle again, but centered at this one point right there. At z equals 0, we had a circle of radius 1. So I'll get rid of that plane and the xy plane. Now at height 1 below, we're going to have a circle who is the same radius as this circle right here. So I'll draw 1 unit below. I'll draw that same circle right there. 1 unit below that, we have a circle of radius a little bit more than 2. So we'll go, here's 1 tick below. I'll draw a circle of radius a little bit more than 2. And then finally, at the z equals minus 3 spot, 1 spot below, we had a circle who had a radius of about 3. And so these are what our different traces look like. If I try to piece these together, I'm getting the impression of something who is round, sort of circling the z-axis, and it scoops in and comes out like this. So if I fill in a little bit more details here, I get the impression of something that looks kind of like a nuclear cooling tower, if you know what one of those things look like. An object who looks something like this. But what if we tried to do the same picture using a different set of traces? Would we have gotten the same image, or at least something consistent with it? Well, let's try this using x traces. So we'll set x equals 0, x equals 1, x equals 2, x equals 3. And let's see what we get here. In these cases, we're going to get the equation x squared minus z squared is equal to 1 for the x equals 0 trace. I know that an equation of the form x squared minus y squared is a hyperbola. So this equation has to be some kind of a hyperbola shape. I also can figure out where it crosses the x, or where it crosses, say, the y, z axes. If z is equal to 0, then the values plus or minus y would solve this particular equation. And so this has to be a hyperbola who's shaped vaguely like this. If x is equal to 1, we have the equation 1 plus y squared minus z squared is equal to 1. The ones will cancel, and we'll get y squared minus z squared is equal to 0, or y is equal to plus or minus z. So this was the x equals 0 trace. This is the x equals 1 trace, 2 lines crossing. If x is equal to 2, we're going to get the equation 4 plus y squared minus z squared is equal to 1, or subtracting 4 from both sides, that's going to be the equation y squared minus z squared is equal to negative 3. Once again, I know that this is the equation of a hyperbola. If I were to set, in this case, y equal to 0, then I can solve that for z equals plus or minus root 3. And so I know that I would get a parabola, or a hyperbola who opens like this. And now I'm starting to sort of see a pattern in this at least a little bit. If I were to go to x equals 3, I should get a higher looking hyperbola. Also, just like before, I notice that I'm going to get the same traces for positive or negative x values, since the x is squared in the equation. So let's try to put these traces together. So now let's plot this in planes who are stacked along the yz axis. So there's the yz plane. Here's x equals 1, here's x equals 2, and then minus 1 and minus 2 will work our way backwards. So putting some tick marks so that I can help adjust where, or I can kind of see where my planes are supposed to be here. So at x equals 2, we're supposed to see this sort of a hyperbola. So we're supposed to go 1.3 units, or 1.7 units up. So I'll draw a curve who goes like this, and 1.7 units down. So I'm going to see that shape. Now I'll remove the plane x equals 2. So we'll go back a step. If I go back one step, at x equals 1, so 1 unit on the x-axis, we were supposed to see in this plane crisscrossing lines. So I'll draw a line crisscrossing here, and then crisscrossing there. And then I'll eliminate that plane from view. Next, when x was equal to 0, we were supposed to see a plane who started at y equals 0 and went its way outwards like this, went right here, and then went its way outwards like that. And then we'll eliminate this plane from consideration. And so now I'm going to go and try to finish the rest of it. One level past this, we were supposed to see another one of these crisscrossing graph shapes. So criss, cross. And then 1 unit past that, we were supposed to see a hyperbola opening up and down. That one's a little bit tougher to do. It's often very difficult to piece these images together. However, if I were to compare them with my original one, if I were to slice this thing straight through the YZ plane, then I would see a curve who looks something like this. And that's completely consistent with the x equals 0 trace. If I were to instead slice this object through a plane right here at x equals 1, I would sort of see it cutting through the object like this. My intuition would have been that those would have been curved shape cuts, but apparently those would have been completely straight lines. And if I were to have gone out here to this point and sliced this object through with a plane, then I would have seen it cut through the sort of outer edges of this shape right down here, which have been consistent with those right there. So it does turn out that these pictures right here are in fact describing the same object. It's just very, very hard for us to visualize it when I'm using the X traces. Well, at least it's hard to put traces together by hand. If we let a machine go, then we're going to see this particular shape. And we really can see that we have the hyperboloid shape the nuclear cooling tower shape. If we let Maple fill in the blanks, then we can see the shape much more clearly. And so at least I know that I got my traces in the z direction right. What about those traces in the x direction? Well, you can't have Maple just specify traces in the x or the y directions. It's just not built that way. But you can have Maple show you all of its different traces at the same time. Now that's pretty busy, I'll be the first to admit, but it shows you all of the different traces that Maple puts together in order to render this picture. But if we were to look straight down this axis, you notice that the shapes that we're seeing are the hyperbolas again. We're seeing all of these different hyperbolas, and you'll notice that as we move farther away from the center, the hyperbolas were opening up at the top, but right along the x-axis, the hyperbolas were sort of the hourglass shape. So that is consistent with our findings. Now, one type of surface that we're going to be particularly interested in is a surface who passes what's known as the vertical line test. What the vertical line test says is that any line who runs parallel to the z-axis only hits the surface at one spot. Never hits the surface at more than one spot. So, for example, this surface that I've just drawn right here would meet this criterion, whereas, say, the sphere we looked at first would not. If I draw a sphere, then any vertical line is going to hit that sphere in two spots, one on its northern hemisphere and one on its southern hemisphere. And that will happen pretty much anywhere unless I hit the sphere right on its equator. But if it happens once, then you fail the vertical line test. So why are we going to care about surfaces who pass the vertical line test? Well, think back to any of your calculus or algebra classes. What made curves who passed the vertical line test so special? It meant that they were the graphs of functions. Think about it like this. Suppose you had a surface who passed the vertical line test. So if we were to go and pick any point in the xy plane, this point right here, then there is one and only one point on this surface connected to this. And no matter where I am, if I were to go and say pick this point over here, this particular xy value, then, because it passes the vertical line test, then there would only be one point on the surface with these xy coordinates. Let's look at that a slightly different way. What this means is it means this. For every point in the xy plane, there is exactly one z value connected to that point on this particular surface. Let's say it one more time to be precise. If a surface passes the vertical line test, then every point xy in the plane is assigned a unique z value such that the point x, y, z is on the surface. This bit right here, every xy is assigned a unique z value, is exactly what it means to be a function, except now we're talking about a function in two variables. This is exactly the description of a function who has inputs in R2, but who has outputs in R. So we're looking at a brand new kind of function. Let's give this sort of a definite name and look at some examples. A function of two variables is a function of the form f, whose inputs go from R2 and whose outputs are in R. Said differently, it's a function who takes ordered pairs like x, y as inputs and returns real numbers like z as outputs. For example, f of xy equals x squared plus xy would define a function of two variables. Given any xy pair, say the point 1, 3, then we could determine the output value by plugging in x equals 1 and y equals 3. This would be 1 squared plus 1 times 3, or 4. Similarly, f of the point 3, 1 would be, well, x is now 3, so we'd have 3 squared plus 3 times 1. That's 9 plus 3, which is 12. Now we could take functional statements like these and turn them into graphical statements. The idea is that we'll treat the input values, the x, y's, as points in the plane, and then we'll treat the output value as a height above the plane. For example, if we took this statement right here, we can interpret the input value as being a point in the plane. So I'll go and I'll grab this point, 1, 3. And then we can interpret The statement f of 1, 3 equals 4 is describing a point in three-dimensional space. There are three numbers, an x and a y, and so it makes sense to treat that last number as z. So I'll draw a point who's 4 units above the xy plane, the point 1, 3, 4. We can also interpret the statement f of 3, 1 equals 12 as describing another dot. We could take this point right here, the point 3, 1. That's the x and the y value, and then we'll associate this final number as the z value. So we're going to get a point 12 units above the x-axis. So that would be really, really high up here. 3, 1, 12. Now we could do this at any random point. Say this point right here, xy. What we do is we'll work out what f of xy is, and we'll treat that as a height. So the value f of xy will be a height, and we'll associate with that with the point xy, f of xy. Now imagine we were to do this for every possible input value here. We take all of the different input values, we get a whole bunch of corresponding dots floating above these things. If we take it together, we're going to get some kind of surface who somehow connects all of these dots right here. What would be the equation of this surface? We know it has to have an equation. A surface in R3 is described by a single equation in the variables x, y, and z. Well, what equation can we use to describe this? We can kind of think about it. It's right here. If you pick a random point in three-dimensional space, the only way it's going to be on this particular surface is if we take a look at its projection down here, and the height of that projection, the z value, had better be the same thing as the output value from the function. So the z value needs to be equal to the f of the input value. And so this equation right here describes the surface who passes through all of the points associated with the function. And so we call this object the graph of f. It's sort of the three-dimensional analog of how we graph a function of one variable by associating x values as inputs and y values as outputs and sort of smoothly connecting them together.
Let's plot the function f of x equals x squared plus y squared. So I'll put up some coordinate axes here, so I have something to work with. Plotting the function means to make its graph, and so the graph is simply going to be the equation z equals f of xy, or in this case, z is equal to x squared plus y squared. And so now I can go back to using the techniques we had talked about earlier for plotting a surface. Namely, I'm going to go and look at traces. In this case, I'm going to look at z traces. So if I were to work out several of the z traces, say the z traces z equals 0, z equals 1, z equals 2, z equals 3, then these would correspond to the equations 0 equals x squared plus y squared, 1 equals x squared plus y squared, 2 equals x squared plus y squared, and 3 equals x squared plus y squared. So once again, what I'm seeing is that the traces form concentric circles in the xy plane, centered around the origin. When x is equal to 0, it's a circle of radius 0. When z is equal to 0, it's a circle of radius 0. When z is equal to 1, it's a circle of radius 1. When z is equal to 2, it's a circle of radius root 2, about 1.4. When z is equal to 3, it's a circle of radius 3, about 1.7. So I see that the circles are starting to pack up a little bit more tightly. On the other hand, if I were to try to go any lower than this, z equals minus 1 or z equals minus 2, I'd get the equations x squared plus y squared is equal to minus 1, or x squared plus y squared is equal to minus 2. Since the left-hand side is negative, but the right-hand side of these equations are always positive, these equations have no solutions. So there are no traces for negative z values. That tells me that the surface never gets below the xy plane. So let me do my best to try to draw these shapes at their relative heights. In the xy plane, at the very, very bottom, I'm supposed to draw a single point. At height z equals 1, I'm supposed to draw a circle of radius 1. So I'll go up to height 1, I'll go out 1 unit, and then I'll attempt to draw a circle centered around the z-axis of radius 1. Now at height 2, I'm supposed to draw a circle of radius root 2, so 1.4. So there's 1.4 units on either side, and I will attempt to draw that circle as best I can in perspective. At height 3, we had a circle of radius 1.7, so it'll be a little longer yet again on both sides.
And so this is what I see. I can imagine that if I added more of these traces, then I would start seeing more and more circles filling in the gaps. And so I would get the impression of something who is centered around the z-axis and round, cup shape, but coming to a point at the very, very bottom. And so if I were to fill in these details, I would have an object who looks something like this. A shape that mathematicians call a paraboloid, but everybody else probably call a cup. Now it turns out that when we were dealing with the graph of a function, these traces that we had found earlier are given another name, language that helps us to identify these. In the language of functions, these are sometimes known as the level sets of a function. The level sets are the curves we find by setting the function equal to a constant and then plotting that particular equation implicitly. So they're nothing more than the z-traces. Nevertheless, a graph like this, which shows me just the level sets, is still a pretty handy way of visualizing a function, even if I can't draw it in three-dimensional space. In the ordinary world, this is sometimes called a topographical map, because we're showing lines of elevation. In a mathematical world, this is sometimes called a contour plot, a plot of the level sets in the xy plane. Once again, I can turn on Maple and have Maple render the contour plot for me. This would be the contour plot of this particular function, and we can see once again the ring of concentric circles right here. And if we put those concentric circles at their appropriate heights, then we do in fact get this shape right here, the bowl shape. If we fill in the blanks, then we get the paraboloid. And there he is, looking straight down into the bowl of it. And so we can kind of see, if I pull it back a little bit, that it does look like a bowl from the sides, but it has concentric circles as its level sets, as its altitude traces. Make a contour plot of the function f of xy equals 2x plus 3y. So a contour plot, this is just that idea of a topographical plot again. So we're going to plot the level sets, or the z-traces of this function. So a contour plot is simply going to be a plot in the xy plane. It's not a three-dimensional plot. We're just going to draw lines of altitude. And so we can get it by finding the different level sets. So the different level sets we get by setting the function, the z value if you'd like, equal to a constant. So we can look at, for example, the constant being, let's say, -2, -1, 0, 1, or 2. And then we'll set this equal to f each time, and we'll see what these things are. Notice that at each time it looks like a constant is equal to 2x plus 3y. Now each one of these things are equations of lines then. For example, the z equals 0 trace, or equivalently, the c equals 0 contour, is nothing more than the line y equals -2/3 x. So this is a line who drops 2 units for every 3 units across it goes, and passes through the passes through the origin in the xy plane. So this would be the contour who corresponds to z equals 0. Similarly, if we were to go and solve this equation, we would get y is equal to -2/3 x plus 1/3. So that's parallel to the original line, but it's just 1/3 unit higher, has a higher y-intercept. And so its trace would look like this. If we took a look at this trace right here, then we would get y is equal to -2/3 x plus 2/3. It's a line parallel to the first line with a y-intercept of 2/3. In fact, it should be kind of obvious now that every single one of the level sets is just going to be lines parallel to the original lines. And so this is what a contour plot would look like. Notice that the contour plot does give us information about the three-dimensional graph. For example, it tells me that the graph is getting higher and higher and higher the farther I go in this direction, whereas it's getting lower the farther I go in this direction right here. If I were going to attempt to turn this into a three-dimensional picture, I might stick the x-axis and the y-axis down here, the z-axis headed straight up, and then attempt to draw these contours at their appropriate levels. For example, if I were to draw that line in perspective in the xy plane, it would be right around there. The z equals 1 contour was originally this line in the xy plane, except that it's been moved up 1 unit. So I'll draw this line moved up 1 unit here. And then the next line was parallel to that, but moved up another unit. And then they get higher and higher and higher as I go. And the other level sets were straight lines, but they went down lower and lower and lower. So if I piece this all together, I get the impression of a plane, something who is completely straight line flat in sort of all these directions right here. Does that make any sense? Well, remember that the graph of this function is nothing more than the equation z equals f of x, or z equals 2x plus 3y. If I move that around, that's 2x plus 3y minus z equals 0. And that's the equation of a plane from one of our previous topics. In fact, it's the equation of a plane who passes through the origin and has a normal vector of 2, 3, minus 1, or might make my life a little bit easier to draw it this way, minus 2, minus 3, 1. If I were to draw that vector, it would be a vector who goes down this way, up this way. So a vector who sticks out something like this. And that doesn't seem completely unrealistic with the kind of graph I've got right here. We can always go through and check our work with Maple. Notice that the contour plot, the set of contours or altitude slices we get, looks pretty much the same as we got before, these lines of slope negative 2/3 crossing the axis. And if we attempt to put them at their appropriate heights, then in fact we do see a plane. And if we have Maple fill in the blanks, then we get the following shape right here. And if I just sort of move it around a little bit, trying to orient it, there we go. Now it's oriented so that the negative axes stick out, and I do see something pretty similar to the shape we drew over there. So what about a function from R3 to R? Could we have such a thing? Well, certainly. I mean, I could make a function whose inputs come from R3, say x times y times z, plus x squared times y, plus y squared z. This would be a function of 3 variables. Give me any input value, say 1, 2, 3, then there's one and only one output value. In this case, 1 times 2 times 3, plus 1 squared times 2, plus 2 squared times 3. So that would get me a grand total of 6 plus 2 plus 12, or 20. How would we visualize a function of 3 variables? Well, it turns out it's not as easy as we might have thought it would have been. For example, let's take a step back. When we had a function of 1 variable, we graphed it by setting it equal to a second variable called y. And so the graph of a function in 1 variable was a curve in R2. We've just been talking about functions of 2 variables, an f of x, y. To graph them, we set this equal to a third variable, z, and the upshot is that we get a surface in R3. So what are we going to do with a function of 3 variables? Well, we're going to have to set it equal to another variable, w, I guess. And then we're going to have to plot it in R4. And that's where everything falls apart. Because whereas R4 makes complete sense from a mathematical point of view, we can't graph anything in it. So this is a little bit like the integration theory for a parametric curve. It's something that we can do. We can talk about a function of 3 variables, but I don't have any ability to graph a function of 3 variables. Nevertheless, there is an important connection between functions of 3 variables and surfaces in R3. Take any surface you'd like in R3. Say this surface again, the one that was sort of the nuclear cooling tower shape, which was a surface who failed the vertical line test, and so it wasn't the graph of a function of 2 variables.
this shape had the equation x squared plus y squared minus z squared is equal to 1. Now, if you stare at that long enough, you'll suddenly realize that the left-hand side is nothing more than a function of three variables, f of x, y, z. So what we have is, this is the graph of f of x, y, z equals 1. But whenever you set a function equal to a constant, this is called a level set. And so what we've just shown is this. Every surface in R3 can be written as the level set of a function of three variables. You could take this one step down. Back in an Algebra 2 class, we're taught that pretty much any curve that you draw can be expressed as some formula that has x's and y's in it. And it might be extraordinarily complicated, who knows what all else is in it. But if it only has x's and y's in it, then it's a function of two variables. And so we can see the same thing right here. Every curve in R2 can be expressed as the level set of a function of two variables. And so this is a nice sort of connection between graphs and level sets of functions of 2 and 3 variables. Let's take a look at this example. Plot the level set of the function f of x, y, z equals 4, where f of x, y, z is the function x squared plus 2y squared plus 4z squared. Remember that all a level set is it's what you get by taking your function, in this case x squared plus 2y squared plus 4z squared, and setting it equal to some constant, in this case 4. And so this gives me a single equation in 3 variables, which is the graph of a surface in 3-dimensional space. Now how should we plot this guy? Well, the best bet for plotting a surface in 3D space is to go by traces, what we've been doing up to this point. So let's go and take a look at its z traces. If we set z equal to 0, we get x squared plus 2y squared is equal to 4. Now I know that this object right here is an ellipse. It fits the standard form, or it fits the form of an ellipse, x squareds plus y squareds with constants running around in it. Now some of you out there might remember the standard form for an ellipse, which helps you to plot them. I'm not going to be that clever. All I need to know is that this is an ellipse, and I'm going to be able to figure out what its graph looks like pretty quickly. For example, if y was equal to 0, this would be the equation x squared equals 4, which means that x has to be plus or minus 2. So when y is equal to 0, x is 2. On the other hand, when x is equal to 0, we get the equation 2y squared is equal to 4. That means that y squared is equal to 2, and so y is plus or minus the square root of 2, or about 1.4. Coupled with the fact that I know it's an ellipse, it has to look like this. So I already have my first bit of graphing right here. It'll be an ellipse who crosses the x-axis at plus or minus 2, the y-axis at plus or minus 1.4, and it lives in the xy plane, because we're corresponding to the z equals 0 trace. Now, if I want to look at any other value of z, say z equals a constant, we're going to get the equation x squared plus 2y squared plus 4c squared equals 4. And so that means that we're going to get x squared plus y squared is equal to some other constant. This tells me that all of the other traces should be ellipses. So I'm going to see ellipses stacked above and below this guy. Rather than trying to plot all of those ellipses individually, I'm going to try to use another trace to help me out. Let me take a look at the y equals 0 trace. Now the y equals 0 trace is the equation x squared plus 4z squared is equal to 4. Once again, this is the equation of an ellipse. So it's an ellipse in the xz plane. I can figure out where it crosses the x-axis by simply setting things equal to 0. For example, if I were to set z equal to 0, that gives me the equation x squared is 4, and so it should cross the x-axis at plus and minus 2. I kind of already knew it was going to do that for my original graph, but it is nice to see that these two things agree. If I were to cross or set x equal to 0, then I would find the equation 4z squared equals 4, which means z squared is 1, which means that z is plus or minus 1. And so in the xz plane, I'm seeing a very long, skinny ellipse. So if I were to go and plot one above and one below, in the xz plane, I'm seeing a much skinnier ellipse going like this. So when I slice the surface flat like this, I see the red ellipse. When I slice the surface flat like this, I see the blue ellipse. And finally, I know that every other slice parallel to the xy plane has to be an ellipse. And so what I get is that all of my ellipses have to sort of touch this little blue shape right here. So all of the cross-sections are ellipses. They fit inside of an ellipse. And that means that my whole shape is going to look something like a smushed down sphere, or, if this is a word, an elliptical sphere. Something who's kind of round like a sphere. But instead of being circular in all of its cross-sections, it's going to be elliptical in all of its cross-sections. Such an object is called an ellipsoid. So there is in fact a word for such a beastie right here. I'm not so much concerned with whether or not you know their names as whether or not you're willing to slice and dice these things and to try to put together lots and lots of level sets, lots and lots of traces to see what these surfaces are. It's very challenging to do by hand, which is a good thing that we have technology to help us out.
For example, if we were to pop on over to Maple and use the implicit plot 3D command, which you can learn about in one of the other podcasts, we would get this picture right here. And based on that, it's pretty clear that I am looking at some squashed object right here. If I were to look at it straight down on the z-axis, then I see that original ellipse across the x-axis at 2 and minus 2, and the y-axis at about 1.4, negative 1.4. Which is consistent. If I look at it in the xz plane, then I see the ellipse across the x-axis at 2 and minus 2, and the z-axis at 1 and minus 1. I can even have Maple put all of the different traces that it used to render this shape. And so you can definitely see that as I look at it from above, all of the different traces are ellipses. And if I look at it, in fact, in every direction, all I see are elliptical traces. So this is our ellipsoid right here, a shape composed entirely out of elliptical traces.